Hello everyone. Another bonus video. Here I want to take a moment to discuss the formula that's used to calculate line integrals of vector fields. So for an example of a physical quantity that would be calculated using a line integral, let's consider this physics concept of work done. Now, work in physics was calculated for a force that was acting on a moving object. If you had a force that was acting on a moving object to increase the object's speed, we said that the work done by the force was positive. And this is the kind of situation that happens if the object is moving in a certain direction and the force's action is kind of aligning with that movement. If the force and the direction of movement are overall aligned, the work done is positive because this force is probably going to speed this object up slightly. By comparison, if the object is moving in a certain direction and the force is acting more or less opposite to that, then the force is going to act to slow the object down. And we would say that the work done in that case is negative. So calculating the work done by a force on a moving object is very important in physics so that you can quantify exactly how the object's kinetic energy, its speed, is changing over time using what in physics is called the work energy theorem. Now, if you're dealing with a very, very simple situation where the force acting on an object is constant and the object is moving in a straight line. So the object's movement can be represented by a straight displacement vector called d. In this special case, the work done can just be found by taking the dot product of the force vector and the displacement vector. And this makes sense, right? Because the dot product was also a measurement of how much two vectors were aligned. The dot product mathematically produces positive values if the vectors are aligned, and the dot product produces negative outputs if the vectors are opposed. So it totally makes sense that work should be the dot product of the vector representing the force and the vector representing the movement. However, if your force is not constant, or if your object is moving along a path that is not a straight line, then this simple formula can no longer be used. So instead, let's try to think of another way to calculate total work done if your force is not constant or if your object is moving along a curved path. So to capture that situation, instead of a single constant force vector, we have a force field, the force as a function of x and y, to capture the fact that you might have different forces acting on your object as it moves through different positions x, y. And instead of having a single displacement vector representing the movement of an object along a straight path, instead here we have a curve C that represents the path along which the object is moving. So here's our curve C, and as we look at the object at different locations, our force field might be acting differently on this object in different directions and strengths depending on where the object is in its journey. To calculate the total work done in this case, we're going to use the usual trick of integral calculus. which is to take this curve C and chop it up into tiny portions. And on this tiny portion of the curve C, we're going to make some simplifying assumptions. Some simplifying assumptions that will lose us a little bit of accuracy and realism, but will enable us to calculate the work done on these chunks much more easily. Okay, so the curve C, representing the object's curved movement, we're going to start by chopping that into very, very small pieces. And if the curve C is chopped into pieces that are small enough, then we can approximate the curve C pretty well using a very small tangent vector. This is very similar to when we were explaining the formula for line integrals of scalar fields. If you parameterize your curve C and you find the derivative of that parameterization, then you will get a tangent vector that is potentially very long. Now, if the tangent vector is too long, then that might give it too much opportunity to pull away from the curve C. So instead, we use this factor delta t to shrink the tangent vector and make it short, and therefore this shortened tangent vector should be a good approximation to a short piece of the curve C. So if we're dealing with a very, very short portion of the curve C, the movement along that portion of the curve is approximately straight and can approximately be represented by displacement along this tiny tangent vector r prime of t multiplied by dt. So this can serve as a tiny displacement vector representing movement along a tiny portion of the curve C. Likewise, if we're dealing with a very, very small portion of the curve C, then the force vectors along that portion of the curve don't have that much opportunity to vary substantially. So if I just took the force vector at a single sample position within that piece of the curve, we can treat the forces as approximately constant within that small portion of the curve. And remember that this notation with the stars is just saying take the force at some random position within the chunk. So, having said that we can treat r prime times delta t, this tiny tangent vector, as our displacement, and we can treat the forces as approximately constant along this tiny portion of the curve, then the work done along this piece of curve can be found by just taking the dot product of this force vector with this displacement vector. The force vector as chosen at a random position in the chunk, dotted with this displacement vector, and we remember when we're doing dot products, you really just have to dot the two vector portions together, and then you can scale the result by delta t. So this is the work done by the force acting on the object as it moves along a tiny portion of the curve C, and therefore the total work done would be approximately equal to the sum of all the work done along these little pieces. So if I wanted to turn that Riemann sum approximation into a perfect calculation, as usual, all I have to do is shrink delta t to decrease the sizes of the chunks of curve that I am working with. And as delta t decreases towards 0, it becomes dt, and I have f at xy with the stars and the subscripts taken away, dotted with this tangent vector as integrated from my smallest t value to the largest t value. And so this would calculate the total work done by this force field acting on the object as it moves through this curve with this parametrization. Now, what we've just written down here is fine, but once again, there is an inconsistency in the variables that are currently present in this expression. This is an integral with respect to t. So as much as possible, I should have everything in the expression written in terms of t. And so what I'm going to do is I'm going to use the parametrization to replace the x and the y in the force field and express those in terms of t instead. Instead of x, replace all of your x's with the x coordinate of the parametrization, and instead of y, replace all the y's with the y coordinate of the parametrization. Make that substitution so that everything is in terms of a consistent variable, just t. And so here we can see that we have stumbled upon the formula that's used to calculate line integrals of vector fields. Line integrals of vector fields are basically saying, look at how much in total your force vectors are aligned with the direction of movement along the curve. And the amount of that alignment is measured by the dot product between the force field and the tangent vector. Take that dot product and then find the cumulative value, find the total amount of alignment by applying an integral, which is coming from this Riemann sum. So this is a little about where this formula comes from.